Welcome. Today we'll be looking at a very interesting topic, that is AC theory, which is also referred to as AC circuits. So here our interest is in studying the behavior of certain circuit components. That's the three major circuit components. That's the capacitor, resistor, and the inductor. Two sources generating time varying voltages or currents. As you know, I'm sure you have heard of DC current or DC voltage. So in DC, what happens is that you have a source that generates a constant voltage or constant current. That is in an ideal case. So in an ideal case, you have a DC source that generates a signal, and over time you realize that our signal remains constant over time. So in DC, the signal, there is no alternating. So if it's positive, it remains positive and constant over time, and the polarity of the signal doesn't change in DC. But in AC, what happens is that the polarity of the signal changes from positive to negative. As you see in AC theory, that is alternating current, we have what we call alternating here. So the term alternating indicates only that the wave form, that is a signal, which is either current or voltage, alternates between two prescribed levels in a set time sequence. So what we mean by that is, for instance, here we have a sinusoidal wave. So you see that the signal starts from 0, then increase to positive V0, comes back to 0, moves to negative V0. So we know that the signal is alternating between two prescribed levels, positive V0 and negative V0. So here we say the signal alternates. And then another waveform, another alternating waveform, as we can see, is this. So rather the signal stays constant for some time here, sharply goes to negative minus 0, and then again moves back to positive 0 and comes back to negative 0. So here the signal is again alternating between plus 0 and minus 0, but in this case there's a sharp fall from positive 0 to negative 0, and then a sharp rise from negative 0 to positive 0. So as you can see from the shape, we call this a square wave. And then another alternating waveform is this. Here we can see the signal gradually moves from 0 to positive V0, and then falls down to negative V0. So from the shape, we call this a triangular wave. So all these three are waveforms. So these are all waveforms, or AC waveforms, because they are alternating. So we call this alternating waveform. So by waveform, what I just mean is that they are, as we can see, they are just the visual representation of how the voltage signal, or in the case where we have current, a current signal changes over time. So as we can see, the nature of it, this changes. This has a smooth change. For the sinusoidal, a smooth change to V0. But in case of the square wave, there's a sharp fall. So there's a sharp changes. So all this, we call them waveforms. They are all alternating current waveforms. But in AC theory, our pattern of particular interest is sinusoidal waveform. So this is the pattern that we will what focus on in what AC theory. The reason is that this type of signal is encountered in vast majority of instances, from the power in your outlet at homes, what you use in your blenders, the power used in most machines. The power that is being generated is in the form of sinusoidal. So that is why we'll be focusing on what sinusoidal waveforms. So as I said, we are particularly interested in what sinusoidal what time varying voltages or current, which simply we refer to as what sinusoids. So here they are simply referred to as sinusoids. So we look at sinusoids. So when we say a sinusoid, what is a sinusoid? Sinusoid is a signal that has a form of sine or cosine function. So any signal having a form of what? Cosine or sine function. That is what we call a sinusoid. I'm sure you know what the sine and cosine functions are, but let's just take a brief look into the waveforms, the sine and cosine waveforms, how they look. So for a sine function, for instance, if you have y being what sine of x and y being what cos x, how do these functions look? Here we have what sine x and we have what cos x. So as you can see the waveforms, you realize that what all these waveforms are what alternating. So here is what 0, here this 0, and then we have 1 and minus 1. Here too 1 0 and minus 1. So for in this case sine x alternates between what 1 and minus 1. The maximum amplitude is 1, and so these are the prescribed levels, 1 and minus 1. The signal alternates between 1 and minus 1, and that is the case for cos x. But for sine x, what you realize that at 0, sine x is 0, then it gets to what? The amplitude 1 at what? 90 degrees, or what? In terms of radian is pi over 2. Then it gets to 0 at what? Pi. Then here is what? 2 pi. That is what? So you realize that the period of sine x is what? 2 pi here. After 2 pi, it starts over again. So it completes a single cycle in 2 pi. And for cos function, at 0, cos is 1. It attains magnitude, maximum value. At 90 degrees, cos is 0. Or what? Pi over 2 is what? 0. Then at pi, cos is what? Negative 1. So it attains negative 1 at what? Pi. And what happens? At 2 pi, it's what? Start all over again. So it completes what? It completes a cycle at 2 pi. So the period of cosine is also what? 2 pi here. So if you understand this, then we move to then look at the general equation of an AC. In AC, what happens is we are either looking at what? The current flowing in the circuit or the voltage at a certain component. So because of this, we look at what? The voltage. So since the AC signal varies with time, we indicate the voltage at a given time as well, V of t. Well, you can also represent it as what? V. So theta. In other places, you can also have it as what? You can just write it as V of t sine omega t plus theta. But keep in mind that even when it's written as V, it doesn't mean it's constant. It still varies with time, as it's a function of time. Or we can also write in terms of currents, phi. Of course, in this case, it's written as current is in terms of cos function, voltage is in terms of sine. it can also be that here we can have what? Cos. Here we can have what? Sine. So now let's look at these individual what? Variables in this equation and what they mean. So here, for a signal, a sine signal, as we saw here, we realize that here the amplitude was what? 1, and here to 1 minus 1. It was alternating between 1 and 1. This is because here we have what? 1 here, because we have 1, and here too is 1. So that's why what? So the amplitude is 1 here. So for that, V0, I0 are what we call what? The amplitude, or the peak value. The peak value of what? Of the signal, that is the current or voltage signal. Then we have omega here, which you know to be what? The angular frequency. Theta and phi are referred to as the phase angle. Here, the entire omega t plus phi or omega t plus theta, they are just arguments to the cosine and sine functions. These are just arguments. One of the important things we look at is the period of the signal. So period, as we saw here, we realize that the period of the cosine and sine functions were just 2 pi here. So depending on the signal that is being given to you, the period can be different. And the period is just the time taken to complete one cycle. So as we saw here, whereas the time taken for it to complete a single cycle was 2 pi. Here too the same, the time taken for it to complete a single cycle was 2 pi here. So for a different signal, you may have different time. And then we have what we call the frequency, F. So the frequency is the number of cycles made in the time of 1 second. So the number of cycles made in the time of 1, so it is just the inverse of what? The period. So the relationship between period and frequency is what? They are inverse. So they have an inverse relation. So F is just 1 over T as a period. So frequency is in hertz or per second, and time or period is in what? Seconds. However, in terms of angular frequency, which is what? Omega is what? Is 2 pi what? F. And its relationship to period, since F is an inverse, is what? 1 over what? T. When we delve deeper into this topic, we'll be talking about what we mean by phase lagging and what? Phase leading. When these two signals are in phase, what happens? What is the value of theta and phi? And when they are out of phase, what is the value of theta and phi? And when they are in what we call the anti-phase or anti-phase, what does that mean? What does that mean when they are out of phase by 180 degrees? Next videos, we will start to delve deeper into the topic by looking at what we call phasor vector diagrams. So phasor diagrams or vector diagrams will enable us to appreciate the phase leading and phase lagging that I spoke about. What does that mean when voltage is leading current, or what does that mean when what voltage is lagging current by a certain degree? What does this mean, and how does that affect our circuit? We want to look at the behavior of the 3 major circuit components. When I mention 3 major circuit components, you know them, right? That is the resistor, inductor, and what? Capacitor. So these 3 major components, passive components, we look at their behavior. How do they resist to the flow of what? Current in AC? what is the voltage across them, what is their reactance, and what is the total impedance of the circuit when all these components are available. So we look at, in resistor, is it current that leads or voltage that leads, or they are in phase. In inductor, is it current or voltage that leads, or they are also in phase. And we also do the same in the case of the capacitor. And we also look at the different combinations. So for instance, we look at the purely resistive circuit. In a purely resistive circuit, we just have a resistor of resistance R connected to a source generating voltage or current. So for instance, here we have a source generating voltage connected to a resistor of resistance R. The source voltage sets up a voltage VR across the resistor to allow current to flow through it. So here we try to determine what the current is and what the voltage is. For purely inductive circuit, here we just have an inductor connected to an AC source. So we try to determine the current and the voltage across the inductor of inductance L. Then we will also look at a pure capacitive circuit. For a pure capacitive circuit, we just have a capacitor connected to an AC source. So here too, we will try to look at the current and the voltage and try to determine which one is leading and which one is lagging. We also try to determine the reactance of all these three components. After we are done looking at this individual purely resistive, purely inductive, and pure capacitive circuits, then we go on to look at what we call the RL circuit, and then the RC circuit. So as from the name RL, you realize that we have only an inductor and a resistor. In the RC case, then we have only a capacitor and a resistor in the case of RC circuit. So we try to find the total impedance in the circuit, their individual reactance, and the current flowing, and then also try to determine what is leading. Is it the current or the voltage that is leading in an RL circuit and also in the RC circuit? Then finally, we go on to look at what we refer to as the RLC series circuit. That is the individual voltages of these components. For the resistor, we have VR. For the inductor, VL, VC, their resistance, and the reactance of the inductor and the reactance of this capacitor. For here, we know that we find out that the inductance of the inductor is omega L, which is 2 pi f L, and here the reactance of the capacitor is 1 over omega C, which is 1 over 2 pi fc. We later see all this, we later drive all these formulas, and then we will understand them very well. After we are done looking at this RLC series circuit and understanding it very well, then we move on to look at what we call resonance in RLC in this circuit. So we look at resonance. Resonance is actually a very important concept we'll be looking at. So what happens to ensure maximum flow? At what frequency must your voltage source be to ensure maximum flow of current in the circuit? So that is where we'll be looking at the resonant frequency and how to calculate it, how to ensure maximum flow of current in an AC circuit. So after understanding resonance, then we move on to look at how to tune a radio set. Then finally, we go on to look at power. As you know, the entire concept of us studying all this is to ensure maximum power flow in our circuit. How do we ensure maximum power flow? Because our desire is power. So in terms of power, calculating the power, we're looking at what we call the instantaneous power. We will look at average power, and then we also look at maximum power absorbed by each of the components. So after we are done looking at all these three concepts, then we go on to look at what some very significant concept, which we call the P factor, called the power factor. In our circuit, our main aim is to push all the power to the resistor, and so power factor will enable us to appreciate how much of our power goes to the resistor. And then we also look at what we call the Q factor, which is the quality factor. So I'll encourage you to go on to the next videos and watch, and if there's any problem, you can please just leave it in the comment section. And thank you very much for staying with us. See you next time.